Good afternoon, dear friends. We continue to study the topic distributed parameters element. Before we start our lecture, I want to ask you to subscribe to our channel, so you cannot miss the appearance of new lectures and examples of tasks solving. In previous lectures, we saw that in the process of solving telegraph equations for a line with distributed parameters, we got the need to find the values of integration constants. In mathematics, so-called boundary conditions are used to find the constants of integration. In the case of a line with distributed parameters, we have two sets of boundary conditions for the beginning and for the end of the line. Therefore, in this lecture, we will find the values of integration constants in the case when the current and voltage at the beginning of the line are known. Then, we will solve the same problem with known currents and voltages at the end of the line. As always, we will end this lecture with conclusions. But first, let's briefly recall what we talked about in the previous lecture. In the previous lecture, we learned that based on the system of equations of the line with distributed parameter for the sinusoidal mode, it makes it possible to form one second-order differential equation with respect to the voltage in the line. This equation is a linear homogeneous differential equation, and we know how to solve such equations. The solution of the equation for line voltage is the sum of two components with unknown integration constants. The propagation of the voltage along the line is determined by a secondary parameter called as propagation factor. The propagation factor is a complex number. Its real part shows the attenuation of voltage or current, and the imaginary part shows how its initial phase changed. The equation for the current in the line includes one more secondary parameter, its parameter called as wave resistance. The integration constants that enter into the equations for the voltage and current can be determined based on the boundary conditions. This will be the topic of our lecture. In our lecture, we will sequentially consider two cases of finding the integration constants when the current and voltage at the beginning of the line are known and when the current and voltage at the end are known. Let's consider the first case. Let us know the current and voltage at the beginning of the line. Let's denote them as I1 and U1 respectively. Consider a system of equations for currents and voltages in the line. It allows you to calculate the current and voltage at any point on the line which is at a distance x from the beginning of the line. At the beginning of the line, x equals 0. So, from the main system, we obtain such system for equations for the unknown constants of integrations A1 and A2. It is not difficult to see that the following expressions are the solution of this system. For A1 is this expression, and for A2 this expression. These expressions allow one to calculate the constants of integration through the known voltage and current at the beginning of the line and through its wave impedance. Let us substitute the found constants of integration into the general system of equations for the line. After simple transformations, we obtain the following system of equations. Note that these equations involve the half sums and half differences of the exponents of the gamma x product. Let's remember the match. In mathematics, such half sums and half differences are called hyperbolic cosine and hyperbolic sine. They are denoted in much the same way as the usual trigonometric cosine and sine, only which the addition of the letter h at the end. You can learn more about hyperbolic functions and their properties, for example, from the corresponding Wikipedia section at this link. Replacing the half sum and half differences of the exponents in this system of equation with the corresponding hyperbolic functions, we finally obtain such a system of equations. Let's consider it more detail. This system allows you to find the values of the complexes of current and voltage at any point of the line if the current and voltage at its beginning are known. This system also includes secondary parameters of the line, the propagation factor, gamma, and the wave impedance. Note that the wave impedance is only used to find voltage from a known current in the first equation and to find current from a known voltage in a second equation. In fact, we can say that the wave impedance is used in these equations in formulas that are Ohm's law. However, the propagation factor plays the most important role in these equations. It is this coefficient that determines how the current and voltage complexes, current and voltage, change as they propagate along the line. That is, when the x-coordinate changes. These equations allow you to calculate the complexes of current and voltage. However, from previous lecture, we know that on the basis of known complexes of currents or voltages, one can easily obtain the instantaneous values. That is, to determine the law of change of current or voltage over time. Thus, the equations obtained allow, in fact, to determine the law of change in current and voltages in the line depending of two variables, the spatial coordinate x and the time. Remember, in the first lecture of this topic, we talk about the fact that all currents and all voltages in lines with distributed parameters are functions of two variables. In our equations, the spatial coordinate x is visibly explicit, while time is hidden in complexes of voltages and currents. We will return to a more detailed analysis of the obtained equations. And now let's consider the second case of defining the constants of integration. As we have already said, the second case of determining the constants of integration is possible when the voltage and current at the end of the line are known. Let's consider this case. Let me know the voltage at the end of the line U2 and the current I2 as shown in this figure. The basic system of line equations remaining unchanged. It is shown here. Note that the variable x in these equations is the spatial coordinate which is measured from the beginning of the line. However, the same spatial coordinate can also be measured from the end of the line. It is shown in detail here in this figure. Let me know the length of the line, L. Then the point with the known coordinate x will be at a distance L minus x from the end of the line. Let's denote the value of L minus x as y. Note also that the end of the line with voltage U2 and current I2 corresponds to the point x is equal to L. We can express U2 and I2 from the main system of equations, substituting the value of the line length into it as a spatial coordinate. We get such a system of equations. Solving it for the unknown quantities A1 and A2, we get such formulas. Such a formula for A1 and such is a formula for A2. Both of these formulas include the exponent of the product of gamma by L by the length of the line. However, the length of the line is known, so the integration constants can be uniquely determined. Let us substitute the obtained values of the integration constant into the main system of equation of the line with distributed parameters. The system after substitution looks like this. At first glance, this system seems very complex. However, by simplifying the products of the exponent and introducing hyperbolic functions, this system can be rewritten as follows. The system that we have received allows us to calculate the voltage and current at any point of the line, which is located at a distance y from its end. In the resulting equation, the spatial coordinate x is clearly visible, and the time is hidden in the complexes of voltages and currents. Note that in both cases, the voltage and current at any point of the line is the sum of the two wave processes. The first process is determined by the exponent of the product gamma and x in a positive degree, and the second in a negative degree. In the next lecture, we will draw very important conclusions from this. For now, let's sum it up. In this lecture, we finally solved the telegraph equations for a sinusoidal signal in a line. Boundary conditions can be used to find the constants of integration. In our case, for the line with distributed parameters, such conditions are currents and voltages either at the beginning or at the end of the line. The spatial coordinate in the first case is measured from the beginning of the line, and in the second case, from the end of the line. Expressions for currents and voltages are the sum of two terms. The study of this fact will help us understand the processes of propagation of current and voltages in the line. The study of these processes will be the topic of our next lecture. Thank you very much. Bye.